10.4. So let's talk about this last slide in 10.4. It's just an interesting question. So the idea is that you're stacking bricks or dominoes. And the question is, can you get to the point where you have a top domino that's completely overhanging the base domino? Overhanging that one right there.
No.
What's your instinct?
No.
Collapse? What's your instinct, Anna? Maybe? Art? You think you can do it?
Because it's.
Give me some food.
Yes.
Yes, he says.
Because it's.
So we've had one of each, a no, a yes, and a maybe. So let's take a look at how the center of mass will work for these. So if we want it to balance, if we have perfectly machined bricks or dominoes or whatever, I'm going to think of each domino as having a length of 2. So there's one domino. And if we position it perfectly so that the center of mass for the upper domino is right on that edge, we'd have this set up. If we do that again, we are going to place this, we're going to set this up in the same type of way so that the top domino is at the center of mass right here. And when we do that, so that we're placing this, we're sort of thinking about this as the next domino there. We need to place that domino under these top 2 so that the center of mass lines up right there. And that is going to create another half of a unit of overlap. And if we keep doing it, what sequence are we seeing? We're seeing the harmonic sequence. So the overhang, here's the overhang. It's going like this. So can we get to a place where the top domino is overhanging the first domino completely? 100%, right? Because this is a divergent series. So you can actually get your top domino as far away as you can imagine from your first domino and not have it collapse if everything is built properly. Everything is machined perfectly with uniform density and all that stuff. And the question then becomes, what's the minimum number of dominoes? Well, right here, we've got 5 dominoes, and it's going to add up to whatever that is. So as soon as we get this number to be bigger than 2, then we've got it. And I didn't add this up before I came into class. I think we need 5.
You did it right there.
Oh, I did. Oh, right there. Thank you. Oh, okay. So 5 dominoes.
You highlighted it too.
I highlighted it too. I didn't highlight the answer. There it is. So 5 dominoes if you do it perfectly. Probably if you go do this in the quiet of your home, you'll probably need 6 because trying to get it to be exactly at the center of mass is super hard. But not intuitive. It feels like it should collapse. As soon as that top domino is over the edge, you would think it would sort of topple over. But infinite series show us that no, it will actually be possible. Okay, does anyone have a question from homework or anything before we go to our next 3 tests?
I do, but it's not about the series themselves. So this one problem is you have to do the, what's it called, function test?
Integral test? Integral test?
And it's, well, the example they do is 2e to the 3k power.
2e to the 3k, like that?
Yeah, over 1 plus e to the 6k.
Uh-huh.
And that supposedly simplifies to an inverse tangent.
Yep. So if you take this term in the denominator, you can turn this into an e to the 3k
Squared.
quantity squared. So that it looks like that. And so you could do a substitution here. There's a couple of ways we could go. We could turn this into a substitution right away and turn these into u's. Or you could go straight to your trigonometric substitution and let this equal sine, secant, or tangent? Tangent. So you could do that, and that will be the quick, efficient way to do it. So then in the denominator, you would have 1 plus tangent squared, which turns into secant squared. And in the numerator, you would have 2 tangent theta. And when you take your derivative, the derivative of the left here is itself multiplied by 3 times dk, if we're going to not switch over to x's, and derivative of tangent is secant squared times d theta. Does that make sense?
Did you do it all the way?
No. Not yet. I want you to try it. Got to get your hands dirty. This is math. Got to get your
The
hands.
example they did, though, they didn't have a secant left over.
Well, there'll be cancellation. When you do your substitution, you've got to solve this, so your e to the 3k times dk is going to be a secant squared. Down here, you're going to have 1 plus tan squared, which is secant squared. And it's going to actually all cancel out, and you're going to get inverse tangent with no secants. Yeah, you'll get cancellation, so the secants will vanish. Yeah. Yeah.
For that e to the 6x is supposed to be 6k.
That should be a k. Yeah, 100% right there. That's a k. It was just it was a sloppy k. Sloppy k. Anything else come up when you were looking at these infinite series? Okay. So let's go ahead and start talking about the comparison tests. There are 2. One is the direct comparison and one is the limit comparison. First, we're going to look at the direct comparison. And we are going to have a little assumption here that we're dealing with positive terms. So we're adding positive numbers together. And we're going to take 2 series, series A sub k and series B sub k. And we're going to talk about their relative size. So let's, in our mind, we're thinking when we compare 2 series, we're going to compare like A sub 1 and B sub 1, A sub 2 and B sub 2. So we're comparing our 2 series term by term. So what we're saying here is that with these 2 series, the A terms are always going to be less than or equal to the B terms. Okay? So what we might say concisely is that the B series is bigger than the A series. Right? If all the terms in the B series are bigger than all the terms in the A series, we're going to think of the B series as being bigger than the A series. Does that make sense enough? So if the B series is the bigger series and it converges, that means the A series, which is smaller than it, must also converge. We're dealing with positive terms. There's no weird oscillation. So we've got a B series that converges, and the A series is smaller than it, so it must also converge. So that's going to be one of our logic points. If the bigger series converges, then the smaller series must converge. And then the other logic point goes the opposite direction. If the A's are bigger than the B's are smaller than the A's, so the B series is smaller than the A series. If the smaller one diverges, the larger one must diverge also. So if we have the smaller series, in this case the B's are the smaller ones, if the B sub k series diverges, so if the smaller series diverges and the A series is a little bit bigger term by term, the A series is bigger, the A series must also diverge. So in layman's terms, smaller than converging converges, greater than diverging diverges. Those are going to be our two concepts there that we're going to come back to again and again and again. So that's called the direct comparison test. So let's take a look at an example right here. So we have a P series, 1 over k squared. That's a P series. It's in the form 1 over k to the P. P is equal to 2. So P is equal to 2 with this. Come on. P is equal to 2 in this case, which is bigger than 1, therefore converge. So we have that convergent series right there. And now if we look at this other series, this series is not a P series. It's P series-ish. It's close to a P series, but a P series is always sum of 1 over k to the p. It's not 1 over k to the p plus a constant. So that's like a P series, but it's not exactly a P series.
If you were to use integral tests on the bottom one, you would get like inverse tangent something.
Yep.
Which also converges.
You
right?
could do this one with inverse tangent. You could use the integral test on this, and you would get convergence. If we can use the comparison test is going to be a lot quicker, we're going to see. So we did a couple like that in the last section where we did use the integral test to do that. And you absolutely can do that. But you'll see that it's going to be faster with a comparison. So do you agree, is it obvious to you that this is true? So if we have 1 over k squared plus 10, is it obvious to you that this inequality is true? So in our mind, you should be thinking bigger denominator, smaller fractions. Right? This denominator, there's our sort of comparison to this. This denominator is bigger than that, so it's got to have a smaller fraction value. Bigger denominator, smaller fraction. So if this series converges, which it does, it's a P series, that means that this series converges by direct comparison. So if we're testing this series right here, we're going to say that so this is going to converge by direct comparison test. So DCT is direct comparison test. Because this statement up here is true. Now, we technically should do a little bit of work to verify that that's true. I want you to have that intuition that bigger denominator means smaller fraction, but that's not the math. Right? That's the intuition. So we want to show this. So I'm going to use this little acronym WTS, want to show. So we want to show that this is true. We know that the series over here is going to converge. So if we can show that the A series is smaller, then we're going to be golden. If the bigger series converges, then the smaller series converges also. So this is very easy to show mathematically. All we do, we put a question mark until we know for sure. We're just going to do cross multiplication. When you have a fraction equal to a fraction, you can cross multiply like that. And then we can subtract off the k squared. And we get to this point right here where 0 is less than 10, and this is true by inspection. So with these comparison tests, you should be able to get to a point where you're just comparing something that's you know by inspection. All right?
It says something about the series has positive terms only. Do we also need to check for that?
No, we're just going to assume that. They're going to tell us that with all of these. If it says use the comparison test, it'll have positive terms. Yeah.
Will they always provide a P of K?
No, we have to find it. We're going to have to find. So, yeah, we'll have to find it. And we'll talk about how to find it in a second. So the B sub k series is the series that we're going to use as our comparison. The A sub k series is usually the series we're analyzing. So the A sub k series is the one that we want to know, does it converge or diverge? I always think of it as A, analyze, that's the one we want to know about. The B is the one that we actually already have information about. So right here, this series, it is P series-ish, but it's not a P series, it's not 1 over k to the p. This is a P series. That is a P series. 1 over k, this is 1 over k to the p. And what is the p value here?
This is campus security for the Westminster campus. A secure order is protected. Remain inside and stay away from doors and windows. Do not
So what do you think the p value is there?
until the lockout order is lifted.
What was that?
In I'm good.
What's the p-value?
Continue. Do not leave
1/2.
the building.
1/2?
Remain
So it's 1 over k to the p, so the exponent on the k is 1/2.
Thank you.
I was gonna say, I was gonna go to the bathroom.
Oh, yeah, no, not now. Not in here. You're locked in for now. I think it's gonna take them less than 10 minutes though, so shouldn't be too bad. All right, so p is 1/2. So now this tells me you know it's a p series. And now we compare this to 1. This is less than 1. And then we make our conclusion. And what's our conclusion if the p-value is less than 1? Then it diverges. So if the p-value is larger than 1, we get convergence. If the p-value is less than 1, we get divergence. The place that's very easy to get confused is that this is the exact opposite result as the geometric series. The geometric series says if we have something less than 1, we have convergence. And if we have something greater than 1, we have divergence with the geometric series. Remember, just note that with the GS, the geometric series, if we have something like a r to the k, let's just pick a to be 1. So if we have something like 1/2 to the k, this is going to converge or diverge. Converge, because that r value is less than 1. And if we have something like 2 to the k, where that's bigger than 1, that's going to diverge. So we have the opposite situation, right? So here, for a geometric series, we call that number r. So you write r equals, then I know you know it's a geometric series. That's less than 1, therefore converge. And down here, r is equal to 2. That's greater than 1, therefore diverge. So just keep in mind that the geometric series and the p series have opposite conclusions. And there's a good reason for that. With the geometric series, this is in the numerator. This 1/2 to the k is in the numerator. The power is in the numerator, right? It's up top. And over here, we're in the denominator. So that's the distinction between the two. That's why the results are opposite, because that's in the numerator, that's in the denominator. Here we're focusing on the denominator. The power in the denominator is 1/2. Yeah?
Why is, for p series, why is it 1 over k to the p instead of just like k to the negative p?
You could write it that way. It's just always easier not to have negative exponents. We're generally going to make less mistakes. 99% of people make less mistakes if there's no negative exponents around. So they just write it in a way that's a little more intuitive. You can see the denominator getting bigger. When someone sees 2 to the negative 50, it's harder to visualize. 1 over 2 to the 50, you can tell, oh gosh, that's a super small number. It just gets a little bit less intuitive when you have negative exponents. But you can write it that way, for sure. Okay, so let's see. Let's finish this one up. So we're up here looking at this one. All right, so we're looking at that thing. This is our a sub k. A sub k is always the one that we're analyzing. This is our b sub k. So when we're doing these comparisons, we're always going to do something like this. I'm always going to start them like this. I want to show this series diverges. So our hunch is that this series is also going to diverge. So in this particular case, I want to show that these a sub k's are bigger than the b sub k's. And you can put greater than or equal to, it doesn't really matter. Greater than or equal to, both will work. So I want to show this because I know the b sub k series diverges. So my hunch is that that diverges also, because the nature of this, that subtraction of 3 is trivial. That's not doing anything to change, converge, or diverge. So that's what we want to show. Bigger than diverging will also diverge. So that's what I want to show. So I take this a sub k, and we are going to compare it. We don't know if this inequality is true or not. This is what we want to be true. Now in our gut, we know it is true because this denominator is smaller than that denominator, so that means these fractions are bigger. That's the intuition. That's not the math, though. Right, so the intuition is this denominator is smaller than that denominator, so this fraction must be bigger than that fraction. So that's the intuition that we, the math should confirm. We want to try to sharpen our intuition, and the math should just confirm our intuition. So once again, when we have ratios, we do cross multiplication. We're going to have this inequality. And we should always be able to get down to two numbers that we can solve by inspection. So we square both sides. We've got that. Subtract off the k.
May I have your attention, please? The drill is over. Thank you for your cooperation. Again, the drill is over. Please resume normal business.
So this tells us then, so we get to a point where this is true by inspection. That's true. So therefore, the original series, you can rewrite the original series. We always call the original series that we're analyzing a sub k. You can call it that. So therefore, this diverges by direct comparison test. Bigger than diverging diverges, smaller than converging converges. So that is our plan. P-series are super important because they are often a series that we use for the B sub k's. Because we can analyze the B sub k series super easily, right? Okay, P is a half, that diverges. So it's super easy to analyze the B sub k if it's a P series. Another one that we might use is a geometric series, because a geometric series we can tell instantly also whether it converges or diverges, right? So P series and geometric series are great series to choose as our B sub k's. Okay. So convergent P series because P is equal to 2, which is bigger than 1. Everyone agree? Yeah.
What if you find a P series that diverges, but the P series-ish is smaller?
Yeah, that's what we're getting to.
Okay.
That is exactly where we're getting to. So we all agree that that converges. Now we're going to look at this. This is P series-ish. This has a bigger denominator, so it has a smaller fraction value. So this is working the way we want it to. We could show this, like we just did on the last slide. We can show that this converges because the a sub k's here, this is what we would want to show. We want to show that a sub k is less than b sub k. That's what we want to show. So we would be taking the a sub k's are the ones that we're analyzing. So we want to show that this is true. We don't know yet. We have to do a little math. But that's what we would want to show. That the a sub k's are smaller than the b sub k's. We intuitively know that this is a bigger denominator, so the fraction's smaller. But the math, we would do cross multiplication. And when we do the cross multiplication, we would get to a point where we have something that's obvious, something that we can say is true by inspection. So if that's true, then therefore we have convergence. Because we showed that our a sub k series is smaller than the b sub k series, which converges, smaller than converging converges. All right. Now, this is what Ari was just asking about. This series here and that series right above it, they're not behaving that differently. Whether you add a 1 or subtract a 1 from the denominator, that's not dramatically changing the series. So it would be a foolish bet that this diverged. You're of course going to take the convergent side of things if somebody asked you. But you would have this dilemma. You would want to show that a sub k is less than b sub k. So you would want to show that this is true to use the direct comparison. And that's not going to be true. This denominator is smaller, so this fraction value is bigger. So we're not going to be able to show this. So this inequality is not going to hold. And we'll get to a point where we can see that by inspection. Subtract off the k's. We get down to here. This is false. So that just means the direct comparison test is inconclusive. We can't use the direct comparison test. So
Not again.
DCT is inconclusive. So we would have to do something else. So the DCT can't be used to analyze a series that is larger than a convergent series. If something's larger than converging, it might converge or it might diverge. And similarly, smaller than diverging could still diverge, but it could also converge. So we can't use the DCT in those two cases. Yeah. So those two cases, we have to go to another test. So in those two cases, we would just say the DCT is inconclusive. Can't do it. So that brings us to the LCT. So for series that we suspect converge or diverge, but they don't meet that inequality condition, so they're not meeting this inequality condition, because the subtraction or the addition is in the wrong direction, then we use the limit comparison. So here's how the limit comparison test works. So we've got our two series. They both have positive terms. No negatives, no weird series. These are all positive decreasing situation, the ski slope. So what we're going to do is take the series that we're analyzing. So here's the one we're analyzing. So this is one we have a question about. This is the one that we know. So B sub k is our base series. This is the one we know. It's a P series that converges or diverges or whatever. So we are going to take our limit of A sub k over B sub k. So we take the limit of the ratio of the terms. And we get this L. If L is a positive real, so a way to write this is L is a positive real, shorthand notation would be that. L is an element of the set of positive reals. So if it's positive real, then series A sub k, series B sub k do the same thing. So if you form the ratio and take the limit and you get a number, that means those two series are linked. Right? They're going to do the same thing. They're either both going to diverge or they're both going to converge. So if you form this ratio and that ratio is a number, that kind of just gives you a sense that they may be moving at different rates, but they're both moving, they're both trending together. They've got a bond. They both converge or they both diverge. And now we've got these two little oddball situations here. And these you are not going to see a lot. I am not going to put these two things on an exam because there's some subtle logic here that's very easy to get confused. But let's talk about it, but it's not going to be on the exam. So let's suppose the limit is 0. So we've got a limit of 0. If the B sub k series converges, and this limit is 0, and the B sub k converges, but this limit is 0, that means the numerator is going to 0 faster than the denominator is going to 0. If the B sub k series converges, B sub k converges, these terms are going to 0 pretty fast, right? For the B sub k series to converge, those ski slope, these B sub k's have to go to 0 fast. But we don't have an indeterminate form here. These are going to 0 and these are going to 0, but the limit is 0. That means that these are going to 0 even faster than the B sub k's are going to 0. So the B sub k's are going to 0 so fast that we have convergence, but this overall limit is 0. That means the A sub k's are going to 0 even faster, which means the A sub k series must converge.
Also, if it's anything else, it's inconclusive, right?
Yeah. Yeah, if it doesn't meet one of these, then it's inconclusive. But it has to be one of these three, though, doesn't it?
Well, like I'm saying.
Oh, I understand what you're saying. Yes, I understand what you're saying. You're saying if the limit is 0, but we have the a sub. Yeah, I understand what you're saying.
So
Yeah.
all of
So
these,
he's saying if the limit is 0, but we don't have that the b sub k series converges. That yeah, exactly. Now I understand what you mean.
so basically
That's
all
true.
of these tests except the integral test can be conclusive.
Yes. Yeah, that's. Yeah, the. I mean, P series is never inconclusive.
But is P series really a test?
I mean, we consider all of them tests, even though like the geometric series and the P series, they're not really tests. You're just checking to see what the exponent or the R is. But a lot of the tests can be inconclusive. There's a whole bunch. But you're gonna encounter this very rarely. But you should at least be able to understand the logic that I'm using there. If this limit is 0, that means the numerator is going to 0 faster than the denominator.
Will we get these examples on home?
Homework, you might see these, yeah. Okay, so let's look at the second one for a minute. So if this limit is infinity, and the b sub k series diverges, so the b sub k series diverges, and all of our terms are going to 0. There's no point in analyzing a series that terms aren't going to 0, otherwise it diverges by the divergence test. So the limit of a sub k is 0, the limit of b sub k is 0. So this series, you're imagining, okay, it diverges, so you're imagining the harmonic series. They go to 0 just slow, but they go to 0, like the harmonic. If this limit is infinity, and these b's are going to 0 so slow that you have divergence, but this is going to be infinity, that means the a sub k's are going to 0 slower. So the a sub k's are bigger than the b sub k's. They're going to 0 slower, so your limit's going to be infinity. So in that case, the a sub k series has to diverge. If the b sub k's are going to 0, but not fast enough to converge, they're going to 0, but they diverge. If this limit is infinity, this means the a sub k's are bigger than the b sub k's. So that means that the a sub k series must diverge also. So it's essentially bigger than diverging diverges, smaller than converging converges. It's just very subtle the way it is given based on this L value. But again, these are not going to be on the test. Those are, I want you to be able to understand the first one here. This one is our primary LCT that we're going to focus on. The other two cases, if you have to analyze them, it'll be on a homework question, and you can look at this, and ask questions and try to reason it out. It's a good mental exercise to try to work those two out in your mind. But in your mind, when you're trying to work these out, we are always assuming that the a sub k's and the b sub k's are going to 0. Right? It's just that these are going to 0 too slow for convergence. Okay, so let's take a look at this. We know that thing converges. It's like 1 over k squared. So it's going to converge. But the first try is with the direct comparison test. That's what we want to do first. So we would want to show for a direct comparison test, so DCT, we would want to show, and we are, okay, over here we're saying that P is 2. Let's just be explicit over here. So P equals 2, which is greater than 1, therefore converge. Okay, so P equals 2. I know you know it's a P series now. You've compared it to 1 and made a conclusion. So you have to have all three of these things here. Identify P, compare it to 1, make a conclusion. So now we know that converges. So we would want to show, if we suspect that this converges also, which we do, if we want to use direct comparison, we would want to show that these a sub k's are smaller than the b sub k's. So b sub k is a convergent series, smaller than converging converges, so we'd want to show this. And the more you do them, the more obvious it's going to be whether this is going to be true or not. So this is what we'd want to show. We, of course, are going to not be able to show that it's true because it's false. we'll get to a point where we have numbers that we can solve the inequality by inspection. So that's false. And false just means that the DCT is inconclusive. So DCT inconclusive. And that's when we jump to the limit comparison. So first we try to go direct comparison. Unless the instructions say use the limit comparison, you always want to try the direct comparison first. And one natural question is, well, if the direct comparison fails, why not just always go to the limit comparison? Well, it goes both ways. Sometimes the limit comparison test fails also. So you generally want to do, and there's more logic involved in the direct comparison, so it's much better to become proficient at this stuff to always go through the DCT first. That's what's going to build your intuition for the series, and when this inequality is going to come out the right way, when it's going to come out the wrong way. So you always want to start with DCT. Now we're going to go to limit comparison test. So the limit comparison test, we take the limit of a sub k over b sub k as k goes to infinity. So a sub k is the series that we're analyzing. So that's going to be 1 divided by k squared minus 1. B sub k is the series that we're comparing to. So in this case, we're choosing b sub k to be 1 over k squared. So if we're dividing by that b sub k, we multiply by its reciprocal, and we have that. So we have the limit of k squared over k squared minus 1. Here's where you have 3 choices.
Yep, it's just 1.
That limit's going to be 1. You can do the whole college algebra thing where you say, oh, the ratio of leading coefficients is the limit because the powers match. You can divide by the highest power of k, and then 1 over k squared goes to 0, and you'd have 1 over 1. Or you could do L'Hopital's rule 2 times. Take the derivative, and you get, actually, you only need to do it once, really, because you do get 2k over 2k. The k's cancel. 2 divided by 2 is 1. So 3 ways to evaluate that limit. Take your pick.
I feel
we
like
get
we
1.
just keep creating harder ways to get the right answer to a math problem.
Why not? So what does that mean then? We got a number here, and we are going to say that this is a positive real. So it's an element of the positive reals. And what's our conclusion if we get a positive real with that limit? Both are going to do the same thing. So since our b sub k series converges, then the a sub k series. So I'll just say both converge.
Is that all you have to write on the test?
Yeah. So this right here would be the work for the limit comparison test. After you showed that this failed. Yeah. That's it, right there.
It's so nice not having to worry about the dx.
No dx, no plus c,
No use of.
no u sub. Is there any question on the logic here? So our 2 basic principles, bigger than diverging will diverge, smaller than converging will converge. Those are our 2 basic principles that we're operating from. Yeah?
This might be a silly question.
Ooh,
but
good.
The only relevance I see that infinite series has to Calc 2 is the integral test. So why are we learning this all in Calc 2? Because I don't see how this goes to anything we've already.
So infinite series are a little bit different than most of what we do in Calc 2. Most of what we do in Calc 2 has to do with integration, for sure. That's our primary goal. Sequences and series are important here. Yeah, you just pointed out that we're doing a lot of Calc 2-y stuff on here with the integral test and doing limits and things. That's all Calc 2 stuff. L'Hopital's rule, taking derivatives. So to show sequences and series converge or diverge, we're using all these calc techniques. You will not see infinite series in Calc 3, but then you will see them in differential equations.
Okay.
So it fits more naturally here because it's a 2-dimensional thing and not a 3-dimensional thing.
Okay.
So everything that we do in here, other than solids of revolution, we're dealing with 2 dimensions. So all this stuff, we're visualizing functions in 2 dimensions. So that's why they put it in Calc 2.
So then why did they teach it in series wow, I can't English today. Sequences and series in Calc 1.
English, please. Calc 1 has enough stuff in it already. And you don't know how to integrate yet. You don't know all that stuff. You don't know all the things that we've done so far here. Like you're just learning integration. By now you're more of an expert at integrating because we've been integrating for another 6 weeks, 8 weeks, 10 weeks almost. But you will not see it again until DiffyQ.
Got it.
And so, and this is, here's kind of, let me ask you a simple question. This kind of gives you a little bit, I don't know if it's an analogy or a metaphor. You guys could probably tell me better than I know. So if you take the real number line and you pick off a number, 2 choices, it's either rational or irrational. What's more likely, picking an irrational or picking a rational?
Picking an irrational.
They're the same.
Picking an irrational is way more likely. 99% of the time, you pick a number off the number line, it's going to be irrational. But we use rationals every time. Like, we're always using rationals. Most of our everyday world is built on rational numbers. Even though, in nature, most of the numbers are irrational. But we focus on the rationals because they're a lot easier to deal with. Right? So now visualize the cloud of all functions. E to the x, sine x, cosine x, all those things. They're in this big cloud. All those common functions, polynomials, inverse trig functions. Another type of function that we're going to throw into that cloud is an infinite series, which we'll do in the next section, next chapter. Most books combine sequences and series in one chapter. This book breaks it into 2 chapters. Chapter 11 is where we do power series. So that's an infinite polynomial, 1 plus x squared plus x cubed, all the way out. So if you imagine that cloud of functions, another type of function, the one that we're going to learn in chapter 11, is called a power series. And it's an infinite polynomial. You can have all sorts of weird coefficients, but it goes on forever and ever, right? It's an infinite polynomial in the sense that the powers go up forever. That's a function. You plug in an x value, you get a single output. And the output is a series. Right? If I plug in a 1 here, I'll get a divergent series. 1 plus 1 plus 2 plus a third, most likely it'll be divergent. I didn't create a pattern that you can analyze easily, but if you plug in a constant, you either get convergence or divergence. So a power series has a whole bunch of infinite series built into one. Every real number will create a series of numbers which we're analyzing. Plug in a 1, plug in a half, plug in a tenth, plug in an e, plug in a whatever. So these are going to be this other category of function in the function cloud. Well, analogous to picking off a number from the number line where it's most likely going to be irrational, same idea with the function cloud. You pick a function out of that cloud, 99% of the time, it's an infinite polynomial that doesn't have like a nice tidy name like sine x, cosine x, e to the x. In nature, 99% of those functions are infinite polynomials that don't have a nickname. Just like the irrational numbers, most of them don't have a nickname. We have a couple of nicknames, square root of 5, square root of 2, e. But most of those irrational numbers have no name, right? They're nameless numbers that are just floating in the real number line.
What's the definition of an irrational number then?
A number so ratio means written as a ratio, a fraction of integers. Irrational means it's not written as a fraction of integers.
Gotcha.
So pi, e, those type of numbers, square root of 2, square root of 5. So those are irrational. You can't write them as a fraction of integers. But those are 99% of the numbers on the number line. Just like 99% of the functions in the function cloud are these infinite polynomials. And so when you solve a differential equation, which is getting empirical data from the world, 99% of the time, the function that satisfies it is a power series and not a simple little common function. So we do that here to sort of build this up so that when you get to differential equations, you're ready to use power series to solve differential equations.
Okay.
Now, in differential equations, you will use a bunch of cooked up examples where you do get sines and cosines and e to the x for the answers. But in the real world, most of the time you're going to get that.
So by this point, we are theoretically fine enough for Calc 3, but we need to get through this for DiffyQ.
Yep. Yep. Yeah, you won't do these things in DiffyQ. I mean in Calc 3.
Yeah.
Yeah, in Calc 3. Okay, so let's look at this one. So first off, Caitlin had asked, what about B sub k? Is it given to you? No, B sub k is not given to us. We have to figure it out. What do you think, what's the natural choice for B sub k here?
The harmonic.
1 over k, the harmonic. So we find our B sub k by getting rid of insignificant terms inside this fraction and simplifying. So up here we get rid of that. That's going to build our B sub k. So we are just creating our B sub k by getting rid of insignificant constants. And so, and this series here, so if we look at our series B sub k, does it converge or diverge? This is going to diverge. This is the harmonic. So you have several ways to tell me that you understand why it diverges. It's totally fine if you say that it diverges and you say that it's harmonic. You could also say P is equal to 1, right? And we know that less than or equal to 1 diverges. So you could do it that way also. P greater than 1 converges, P less than or equal to 1 diverges. So whatever your preference is, you can think of it as the harmonic, which diverges, or you can think of it as a P series, which also diverges because you've got a P value that's less than or equal to 1. Okay, so that is our comparison series. That's our base series. When we think about this series, is the A sub k series, this is A sub k, is the A sub k series bigger or smaller than the B sub k series? Smaller. So this A sub k has a bigger denominator, so it has a smaller fraction value. So this is smaller than this, smaller than diverging. Who knows, right? Smaller than diverging, you have to do more math. Smaller than diverging is not conclusive in any way. It's inconclusive. But let's just show that with the DCT. So if we were going to do DCT, because B sub k diverges, our hunch is that this diverges, we would want to show that A sub k is bigger than B sub k, because bigger than diverging diverges. But we're going to see that this is not going to happen, that this is going to be inconclusive. So we would, for the direct comparison to work, we would want to be able to show this. This is not going to be true. We cross multiply. We get to that. We get to a statement where we can solve it by inspection. This is false. So because that's false, that means DCT is inconclusive. So therefore, inconclusive. The DCT is inconclusive. So that means go to the limit comparison test. So DCT is inconclusive. We're going to go to limit comparison test then. So we're going to go to LCT. So this is to find the limit as k goes to infinity of A sub k divided by B sub k. So the one we're analyzing divided by our base series, the one that we know. So we're going to get the limit. A sub k is the one we're analyzing, 1 over k plus 1. And if we divide by B sub k is 1 over k. If we divide by B sub k, we're going to multiply by k over 1. Once again, we know what this limit is. We have polynomials with the same degree, the same order. So all we have to do is look at the ratio of coefficients. You could use L'Hopital's rule. You could divide by the highest power k, 3 ways. So here's where we have to be super careful. We have to make sure we understand the conclusion of the limit comparison test. First off, we're getting a constant here. And the important thing is that this is a constant that is a positive real. So that tells us that both series do the same thing. So in other words here, because we chose a B sub k that diverged, that means that both the A sub k series and the B sub k series, both of them are going to diverge. So that's a positive real, therefore both diverge. So there's our conclusion. Direct comparison was inconclusive. Limit comparison, as long as we get a positive real there, we can conclude that the series do the same thing. All right, questions on any of the logic or any of the steps that we are using for the inequality demonstration? Whether we demonstrate that it's false or true? Anything that you're not sure about? So this is about the time where, up until we get to the comparison test, usually most people are feeling, okay, I got this series stuff, this is okay, it's okay, it's okay. And then all of a sudden there's like, whoa, this one's going faster than that one, this one's going slower than that one. Oh wait, is it a P series or is it, like there's all of a sudden it feels like we're juggling 5 balls instead of 3.
Was that 6 and 7?
This, 6 and 7?
Yeah.
Yes. Yeah, I think we're at 6. Out of the 10 tests, if we call them tests, this is 6 and 7.
What's the hardest one?
We've already done the hardest one.
What is it?
Integral test. Integral test is the hardest. Because you have to usually use an improper integral that usually requires, thinking that's...
And how many
These are more prescriptive.
integral test problems will you put on the test?
How many integral test problems?
Yeah.
1. 1 will be enough. When there's 10 tests, you can't do more than 1 of each. Okay, so I'll do this first one, then you guys can try the, well, let me think about this. Which one of these are you more likely to be able to do? Let's let you all try this one. So try this one first with direct comparison. So find your B sub k series, and then try direct comparison to this. So find your B sub k first. I'll give you 2 minutes to at least get started, think about your B sub k, and then I'll confirm what B sub k should be just in case don't want you to go down a rabbit hole. So B sub k, what are you going to choose for B sub k? Remember a couple slides ago, rule of thumb was get rid of anything insignificant and simplify. That's how you create your B sub k.
That's supposed to be a k, but it's not.
And then simplify. Yeah.
Let's see if I remember how to simplify things.
Yeah, all those rules of exponents. That is a pretty nice dragon.
Dang.
It's a lot more complicated than a swan.
Where'd you see that?
This is over on the chalk table. There. Swans I used to be able to do. Dragons? Wow. That's pretty cool.
That's kind of crazy.
So let me just point out that the B sub k that you should be using, you get rid of anything that's insignificant, like the addition or subtraction of a constant, and then simplify. So this is the B sub k that you should be using. So then go from here. Laws of exponents. B sub k, not of. So, does your B sub k series converge or diverge? Convergence. So if you know your B sub k converges, then we're hoping that the A sub k converges, so we want to show that A sub k is smaller than B sub k.
That's
So-
what we're hoping, so even if we know that it's bigger, we
Yeah.
still have to write.
Yeah, exactly. Right, exactly. So this one converges, or that one converges. Yeah, this one converge. We want to show smaller than converging converges. Usually I would write the A sub k first, because that's the one we're trying to think about. I would always put the B sub k on the right, because that's the one we know. So if the B sub k converges, then we want to show, if possible, that A sub k is smaller than B sub k. They both go to the numerators.
But you changed it.
It shouldn't, so you can think about just doing multiplication twice. If you multiply both sides by this, it goes up there. If you multiply both sides by this,
Still stay greater than.
yes, because you're not doing any negative, you're not multiplying by any negatives.
Okay, so zero.
Yeah, but this should go that way. This should go up to here. So that goes to this numerator and this goes to that numerator.
Wait, is that, is this, oh, this is negative.
Oh, you mean a negative exponent?
Yeah.
I wouldn't think of it that way. Just think this is in the denominator, so if you multiply both sides by k to the 3 halves, it would cancel here and end up in the
So
numerator
how do we
here.
know what we're supposed to do?
It would be k to, this would be k squared plus 3 over here. Because you're multiplying,
Because all the A's were.
Yeah,
K's.
that's what
Oh,
so you're multiplying both sides by this first, multiply both sides by that, and that's gonna stick this one into the numerator. Then you multiply both sides by this.
Oh, just that.
Yeah, that.
See, it's just the inequalities, and like, everything's getting more.
Statement of
Well, I
facts.
think we need to get to a point where one is still in the numerator. And
Okay.
algebraically, we can manipulate
Yeah.
the expression.
Sounds good.
Somehow by maybe,
We'll do it up here now.
Oh,
I trust you.
I think I goofed up though.
Oh, do you?
I have a thought to stop writing just the wrong numbers.
That can happen.
Why did I write 2?
Your pen just starts writing random things. So I think, I saw everybody got at least to this, got to here. Everybody agree with that? So we're dealing with the p-series, that p-value is bigger than 1, so that means converging. P-series converge if p is bigger than 1. So then what we would want to show, I always am going to put b sub k on the right, a sub k on the left. Always, for this comparison thing. Because this is the one we're analyzing. And so we're thinking to ourselves, the one on the right, that one's converging. So if that one's converging, I want to show that the other one, the one we're analyzing, I want to show that it's smaller if possible. That would be direct comparison. So direct comparison test, if it was to work, we would want to show that that's true, that the one we're analyzing is smaller. And so then we go through the math here, and we see whether we can do that or not. We don't know, so we put a question mark here, not sure. This is going to be 1 over k to the 3 halves. And then we cross multiply. So this k to the 3 halves is going up to the left. So that k to the 3 halves goes up to the left. So it's going to be k to the 3 halves times k to the half, which is k squared. This k squared plus 3 goes up to the right. So we're going to get k squared plus 3. We're going to subtract off the k's. Oh, this is true, huh?
Wait,
Wait, where?
why wouldn't it be k to the 3/4?
Did I add wrong? So k to the 3 halves times k to the 1 half.
Oh, it adds.
We add, so the 3 halves to added to a half is going to give us 4 halves. So k squared on the left. And when this comes up to the right, that stays as k squared plus 3. So that's true.
DCT.
DCT works. So therefore, both converge. So both converge in this case. Break. Oh, question first.
I was gonna say for AK, is it a good habit to just leave, or is AK always gonna be that?
A sub k is always going to be whatever this is. This is always A sub k. A sub k is always from the series that we're analyzing. It's the series that we're trying to figure out whether it converges or diverges.
So BK is the only like one that you have to worry about.
B sub k is one we create. B sub k is the one that we create, but we create it not out of thin air. We get rid of insignificant constants and then we simplify it. So B sub k is created with that deliberate process. So we get rid of anything that's trivial, anything that's insignificant, adding or subtracting constants.
They should have switched the line. It could have been like artificial K. No, that's the one you're making.
I mean, A sub k, I don't know, yeah, we could let A stand for something different. Yeah. All right, let's take a 10-minute break, and then we'll do a few more of these. And then we'll get to the alternating series test. Ooh la la.
Jim?
Yes.
For the.
See, like, you get the one before you check.
Okay, let's move on to this one.
Oh, yeah, so yeah.
So this one looks a little different. What kind of series? Let's do one thing first. Let's find our B sub k, and then we'll talk about what this series is. So B sub k we always find by getting rid of the insignificant terms. So the insignificant part there is the addition of 3 in the denominator.
Looks like a GS.
So everybody know what kind of series that's going to generate? What kind of series is that? So it's in the exponent, and we don't call them exponential series, we call them geometric series. Yep, but that's right. So this is how we would write it in order to make sure we identify R properly. All right, geometric series is A R to the K, arc. So instead of a P, we have an R, and R is what in this case? 1/5. Just like the P series, we compare it to 1, but our conclusion is vice versa. Smaller than 1 for a GS, converges. Smaller than 1 for a GS converges. So our suspicion is that the A sub k series does the same thing, also converges. So if we're going to use the DCT, we would want to show that A sub k, let's put the A sub k and the B sub k there, alphabetical order. Do we want to show that the A sub k's are smaller or bigger than the B sub k's if the B sub k's converge? Smaller. Yay, smaller. So again, our principle, smaller than converging converges. So if we can show that, then we're golden. Let's see if it's possible. So the A sub k is whatever we started with. We don't know, so we put a question mark over it. We don't know. We want to show that it is less than the B sub k, which is 1/5 to the k. We cross multiply, so we multiply both sides by 5 to the k. We multiply both sides by 5 to the k plus 3. So we get that. And that plus 3, of course, is not in the exponent. It's down here. And we get to a numerical inequality that we can solve by inspection. This is true. And if that is true, we are done. We just have to make our conclusion.
Wait, why 0 and 3? That's the same thing as the last answer.
0 and 3. Oh, no.
It's almost like -112.
Therefore, both are going to converge. Yeah, we had 0 and 3 up there, too. Oh, man, interesting. Well, 0 is still less than 3. Any piece of that that you're not enjoying? Wait, no, I didn't ask that. Any piece of that that you don't understand?
Would we be able to make the whichever like number or function that we're using with k just to 0 whenever we're comparing them?
Where are you at? Where are you looking? Up
So that second to last step.
here?
Just right above.
That?
Yeah, would we be able to, like, regardless of whatever it is, as long as they're both equal, we can just make them 0?
Yeah, we'll subtract them off from both sides. Yeah. They should, I mean, in most cases, they're going to line up nicely and they'll subtract to 0. There's some cases that will be a little more complicated that won't be quite so nice, but in most of the cases. All right. So 2 to the k is not insignificant in and of itself, but 2 to the k is going to be a lot smaller than 3 to the k. If you were to graph those two exponential functions, 3 to the k is an exponential, 2 to the k is an exponential, 2 to the k is going to grow slower than 3 to the k. 3 to the k is going to grow a lot faster. So if we have to choose a b sub k for this, if we want to try to use comparison, we are going to choose our b sub k to be that. All right, so you all take it from there. Decide whether your b sub k converges or diverges, and then see if you can use the direct comparison.
Well, it's just because, like, on a conceptual level, I don't understand something. Like, I get all the formulas and I get everything, but it's like, yeah.
Yep.
Yep.
All right, we'll get there. We can do that then.
Thank you.
Well, plenty of time. We have an hour. Hopefully it'll take less than an hour.
I remember those graphing problems in Calc 1 that took 45 minutes.
I know. It's going to take a while.
To think that that would just be a walk in the park now.
I know.
Jim?
Yep.
When we're working through these, do you want us to have these question marks over our?
There, we want to show that that's true. Here's where the question mark shows, because we don't know if this is true or not.
So if we're setting this up, you would always want us to.
We don't do it there.
Oh, no, not.
Because that's what we want to show. We want to show that the A's are less than the B's.
Okay.
So the question then is, we don't know, are the A's less than the B's? So here we don't know. So there we should have a question mark, because we don't know if that's true or not.
And that's for every
All
single step.
the way down to the end, yeah.
Would you penalize us for putting a question mark in the wrong place on an exam?
It depends on where you put it. Like if you write square root of question mark,
Well, you know what I mean, like, in terms of the inequality.
no, I wouldn't. Like if you wrote A sub k question mark less than or equal to B sub k, you could argue that you're asking, is A sub k less than B sub k in this case? Yeah, no, that's fine. What kind of series is this?
Geometric.
Geometric again, right? We have the k in the exponent position. What is the r value? 1/3. So if we were to write this in traditional geometric series form, we write it like this.
Yeah.
And the r value is 1/3. This is less than 1, so our conclusion is converge or diverge? Converge? So for a geometric series, less than 1 converges. 1/3 times 1/3 is a 9th, times 1/3 is a 27th. That goes to 0 very fast. So we have convergence. So then we do our want to show. All right, we want to show we've got our A sub k, we've got our B sub k. B sub k is coming from down here where we have convergence, so we want to show A is less than or greater than B. Less than. So then we have the A sub k from there. We don't know, is it less than? This is what we're trying to show. B sub k is what we chose, so 1 over 3 to the k. Then we do our cross multiplication. So the 3 to the k goes up to the left. The other denominator goes up to the right. And then we subtract off, and we get 0 less than question negative 2 to the k. And if we want to get rid of the negative, we could just add this to the other side if that's easier to analyze. Is that true or is that false? False? Right. This is false. So if this is false, this means that the direct comparison test is inconclusive. It's inconclusive. So when it's inconclusive,
Somebody needs to go tell the bee to shut up. There's classes going on.
so when it's inconclusive, we're going to go to the limit comparison test.
Imagine if that was your phone ring.
Right? Room. So limit as k goes to infinity of a sub k over b sub k. That's the limit comparison test. So let me put LCT just to emphasize. We are now doing limit comparison test because DCT is inconclusive. DCT inconclusive. So a sub k is the original. It's the one we're analyzing. So it's 1 over 3 to the k minus 2 to the k. 1 over 3 to the k minus 2 to the k. Divided by b sub k. Dividing by b sub k, which is a fraction, means multiplying by its reciprocal. So we get 3 to the k over 1. So we're trying to evaluate this limit. 3 to the k divided by 3 to the k minus 2 to the k. That is indeterminate. So the simplest way with these limits, you could start taking derivatives and using L'Hopital's, but it's going to be a real mess and maybe not get you anywhere. If you just divide by the dominant term, so when you had rational functions, you took the highest power of x and divided by it. Instead, we're just going to pick the dominant term. 3 to the k dominates 2 to the k, so we're going to divide everything by 3 to the k. If we divide everything by 3 to the k, we get this. So we're dividing numerator and denominator by 3 to the k. So if you divide both, we're going to get that. 2 to the k divided by 3 to the k is 2/3 to the k. And what happens to 2/3 to the k as k goes to infinity? Where does it go? 2/3 to the k goes where? 0. Right, that's geometric. Number smaller than 1 multiplied by itself gets even smaller. So this limit is 1. Lots of 1 limits. It's based on how we built b sub k, because b sub k is closely related. Unless we have like funky coefficients in the original, we're going to end up with a limit of 1 quite frequently. So what's our conclusion? That is a what kind of number? Positive real number. So it's a positive real number. So that means that both these series, the a sub k series and the b sub k series, they do the same thing. So they both converge. So both series, both are going to converge. Both converge. All right, any questions there? All right, you all try this one. So same idea, there isn't an insignificant constant to get rid of, but square root of x grows way slower than k grows. So this, your square root of k is going to be insignificant relative to what else is in here. And you might even say, let's get rid of the 2, because multiplying by 2 is kind of insignificant. And it'll be interesting to see what happens. So you could get rid of the 2 too, because multiplying by a constant doesn't change anything. My recommendation is to use b sub k, leave the 2 in there. So take it from there. There's your b sub k. Bless you. So decide whether the series b sub k converges or diverges. And then set up your DCT. You can conclude, yeah, you could factor out the 2 and say that it's a divergent harmonic. Yep.
So technically speaking, we're not really outgrowing growth rates at this point
We're not out. What do you mean?
in terms of math knowledge.
We're not doing what with them?
We're not using them.
I mean, we're using them intuitively right now. We don't formally use them unless we see a factorial or a power tower. So you could choose your b sub k to be 1 over 2k or 1 over k. It's not going to matter. There will be a slight difference in the execution. So is your b sub k series converging or diverging?
Diverging.
So there's a couple of ways you can say this. So this series then, you can factor out the 1/2. So there's your series. So you could say p is equal to 1, which is less than or equal to 1, therefore diverge, or you could say it's a harmonic, so therefore it diverges. Either way. Greater than 1 converges, less than or equal to 1 diverges.
So, Jim, did I show this work correctly then, or?
Yeah.
Okay.
Good. That's right. Perfect.
Even leaving this 1 over 2k?
Mhm.
Okay.
Yeah, that's fine.
Okay.
Because you're essentially just popping this out to the front and leaving that as a you're analyzing this.
Yeah.
So yeah, that's fine.
Okay.
All right, so do your DCT. See if you can get it to work. DCT. Did it work? Is that a 2 to the k on your left? Yeah, 2k.
That's 2
Where's that?
Oh. That's what was.
Thin air?
Yeah. Okay.
Oh, somebody has a new method.
New method. The Harrison method is rubbing off on actually.
Yes.
I was thinking on the last part, you could just make it 1 over 1 to the k.
Make it 1 over 1 to the k. Does 1 over 1 to the k converge or diverge?
Okay, that's negative. Some things that only a math nerd would ask.
Some things are only understood in a math classroom. So we've got a b sub k that diverges. Everybody agree with b sub k diverging? Yeah. So does that mean we want to show a sub k is bigger than b sub k, or a sub k is smaller than b sub k? Bigger. Bigger. Principle, bigger than diverging diverges. So that's what we would like to show. that A sub k is bigger than B sub k. Because we already showed that B sub k diverged. So the part where we don't know then, so we're going to put a question mark here. So 2 times k minus the square root of k, is it greater than, or you don't have to do equal to, greater than, it's fine. So B sub k is this. So let me point out that if you were to choose your B sub k to be 1 over k instead of 1 over 2k, which you could argue is a fine thing to pick, then you're not going to get the cancellation that we're going to have in the next step, which would make it harder. So leaving the 2k in, leaving that 2 in, makes this step easy, because then the 2k's cancel. If you had this as a 1k, you'd have a k and a 2k, and it wouldn't cancel, and it would be a little bit harder. So we have this, and true or false. So if you don't like the negative there and you want to, get rid of all negatives before you make any decisions, you would have that, and that's true. Principal square root, positive square root, that's a positive number. It's bigger than 0 for sure. That means that both series do the same thing. And since the B sub k series diverges, both diverge. Both do the same thing. Okay, now let's look at this oddball. We certainly expect that to converge because we see that power of 2 and natural log of k is making it grow even a little faster in that denominator.
Could you also do that with the integral test?
Yep, you could try this with the integral test for sure. Let's see if we can do it with comparison test. So the choice that makes the most sense is to think about natural log of k certainly is making the denominator increase, but it's not adding a ton of speed to that increase. And we know that if we just look at 1 over k squared, that that's a p series that converges. So let's go that way. Let's just see if that b sub k is a good b sub k, if that will work. So we're going to want to show, let's see, a sub k, b sub k. What do we want? A is less than b's or a is bigger than b's? A less than b? Smaller than converging converges? So let's see if this will pan out. So here's where we put our question. We don't know. Is that true? And sure enough, we will see that this is true when we do our cross multiplication. When we do our division by k squared, natural log of k bigger than 1? That's true. Now, technically, we look back at our index, and it does start at 2, and natural log of 2 is bigger than 1. Or is it? Wait, what's natural log of 2? Someone type in natural log of 2.
Yeah, 0.69.
0.69. Is that bigger than 1?
Great answer.
So 0.69, so it's not bigger than 1, but what
Constant.
happens when you get to 3? Right, we know the natural log function is going to do this. So maybe this isn't true for a couple of leading k's, but eventually, in the tail, it's certainly true. So this is true as long as k is bigger than 2. So this is true enough. If it's not true for 1 or 2 or a finite number of values, no big deal. This is true for the k's in the tail. So we can chop off the, chop off the head.
Some of us in here would really like it if it's true enough.
Say that. What's that?
Some of us in here would love it if it's true enough.
True enough. Is this true? It's true enough. It's true enough.
Will you give us an extra point if we put in that?
If you put that in there,
Yeah.
Ooh.
depends on the rest of the test. If you need the extra point, maybe. Therefore, both
But
do
if you
the
miss
same
the extra
thing.
point.
Therefore, both converge.
Congrats, you got the extra
Both converge.
At 29%.
Yeah, all right.
Why is it when k is greater than 2 but not greater than 3?
Natural. Oh, should I be saying greater than 3 here?
I said e.
Oh, but I mean, yeah. But k is an integer.
So is E.
K is an integer, so greater than 2 means 3 is the least number that's greater than 2.
Oh, okay.
So since k is, but yeah, if we were dealing with real numbers, we would want to be greater than E, greater than 2.7 there. But because this is all integer valued, we're only ditching the first term. We're only ditching k equals 2. K equals 3, this will be true. Yeah. Okay, so that is that. Choose your own test. Use the test of your choice to determine whether the following series converge or diverge. Bless you. Okay. So, first step, see if you can write this in sigma notation. So that's the first step. Spend 30 seconds, rewrite that in sigma notation.
Will you put questions like that on the test? Like choose your test?
No, I'm going to tell you what test to use, just because in a testing situation, it's easy to panic. It's much easier to be, if you're told to use the integral test, you just know where to start. Trying to triage and figure out what test makes the most sense is hard. All right, so first, see if you can write that in sigma notation. In Calc 2 notation. Does anyone have it yet?
Is it k over k plus 1 to the k plus 1?
Yes. So everyone agree with that? K over k plus 1 raised to the k plus 1. Is there any mysteries there? Okay. So this is one of those ones we should always, even though we haven't really done it today because we've had specific instructions to use DCT, but we really should also in the back of our mind be thinking about the divergence test. Right? We should always be sort of thinking, is the limit of base of k 0? If it's not 0, we know it diverges. So when we look at this is one of those funky ones. The limit of base of k here is indeterminate. It's 1 to the infinity. 1 to the infinity is indeterminate. So we had a technique to evaluate those indeterminate limits called the log limit process, right? That's how we figured out indeterminates. But we did have a shortcut, didn't we? We had, I think we went through this, right? We went through, if you have something of this form, where does this go as k goes to infinity?
E to the b.
This goes to close e to the
K.
Nope, not k. K is going to be gone because k is going to infinity. E, there's no n there.
X.
There's no n.
It's an X, guys.
There's
It's
no
not an
n's.
N.
There's no x's.
E to the A?
E to the
E to the a times b.
Oh.
So if both of these, if you have a constant in both of these positions, this is our shortcut. If you already, now when you're doing homework, I would be doing the log limit process for sure to make sure you can do it, because you have to do that on the test at least once. But if you're already comfortable with log limit process, this is our shortcut. If we can put it in that form, that's what the limit is. You prove that with log limit. Now, we have to be a little clever here to do that. But if we can get it into that form, it would work. So, should we do log limit just as a refresher since we haven't done that in a week? And then let's talk about maybe how we could do the shortcut. So let's do a log limit. We haven't done one in a while. So the idea is that we are going to build a function. Now, normally we would change it over to x's because we're going to have to do some derivative stuff at some point. So we have that. So there's our function. And the question is, what's the limit of this function as x goes to infinity? So we take the log of both sides and the limit of both sides. On the left, the log and the limit are going to look like this. So we push the limit inside the log because the log is a continuous function. And on this side, we have the limit of, when we take the log, we pull down the exponent, and we have that. So the log of both sides, the log of the right-hand side allows us to pull down the exponent as a coefficient. So the heart of this is figuring out that limit on the right-hand side there. And so our technique that we've used repeatedly is to push. If you look carefully, where does this go as x goes to infinity? This one here goes to natural log of 1, which is 0. And this one goes to infinity. So that's indeterminate. Infinity times 0 is indeterminate. Depends on which one goes to its respective limit faster. So what we have been doing is shoving that one in front down into the denominator. Multiplication by x plus 1 is the same as division by its reciprocal. Can everyone agree now that this limit is a 0 over 0? And it's 0 over 0. So we use L'Hopital's rule. In the numerator, we take the derivative. In the denominator, we take the derivative. Not a quotient rule, though, right? Just derivative top, derivative bottom. The derivative of the numerator is the derivative of a log. The derivative of a log is 1 over the inside. In other words, take the reciprocal of the inside. 1 over the inside multiplied by the derivative of the inside. Now here we do use a quotient rule because we're taking the derivative of the inside, which is a quotient. So here we use the quotient rule, so we're going to go low times the derivative of the numerator, low d high, minus high, which is the numerator, x, times d low is also 1, all over the denominator quantity squared. The derivative of the denominator, we treat that as x plus 1 to the negative 1. Its derivative is negative x plus 1 to the negative 2. And there's some quick cancellation here. X plus 1 squared here is going to cancel with x plus 1 squared there. And when this flips over, when that flips, that x plus 1 squared is in the numerator, so it's going to cancel with that x plus 1 squared in the denominator. So let's see what's left here. So we have a limit. We'll write it as a product here. That's x plus 1 over x. That minus sign is going to come into play in a minute. We'll get to it when we need to. So x plus 1 times 1, that's just x plus 1. X plus 1 minus, x times 1 is just x, so x plus 1 minus x is just 1. So that's 1. And all of that's 1. And down here we have this negative 1. So now we can take the overall limit. So this is a constant, negative 1. Limit of a constant itself. What's the limit of x plus 1 over x? 1. So the overall limit is negative 1.
That's crazy.
So on the left-hand side, we have natural log limit y. On the right-hand side, we have -1. So we can make a conclusion. Therefore, limit of y is
E to the negative.
e to the -1. 1/e.
Oh look, another fraction.
Another
Almost
fraction.
like -1/12.
No, nothing like -1/12. Nothing like it. It's positive. It's irrational. It's a whole bunch of things. So that is the limit of a sub k. So what's our conclusion? Let's not lose sight of the what's.
Convergent.
Yep. If it's not convergent, why does it diverge? Because the limit of a sub k is not 0. Right? Divergence test says if the terms in the series aren't going to 0, you instantly know it's diverging. Because in the tail, you're adding 1/e plus 1/e plus 1/e repeatedly forever. So this is going to diverge. So therefore, diverge by divergence test. So there is our conclusion. Yep, divergence test says the only way a series can converge is if the terms go to 0. If the terms don't go to 0, it must diverge. Because in the tail, you're adding 1/e to itself repeatedly. And if you take any positive number and add it to itself repeatedly forever, that goes to infinity.
Doesn't that mean if you have to do a log limit, it will always fail to diverge? Because you can't have e to something that's 0, right?
So you're saying that this indeterminate form 1 to the infinity can't be 0?
I'm saying if we have to do the log limit.
And we do log limit when we have 1 to the infinity.
Okay.
And that's a fantastic question. And off the top of my head, I feel like that's true. I feel like that's true. If it's 1 to the infinity, how could it possibly be 0?
So if we use log limit, it will be divergent.
Yeah, that's a good point. I'm going to look at it more carefully. I can't think of an exception where there would be some weird scenario, but that feels correct.
We should use that on the
Yeah, that
test.
feels correct.
Yeah, it can read.
No, you still got to do the math. You got to do the math.
No.
We shouldn't have
Yes,
asked.
do the math. That's the fun part.
Shouldn't have asked.
Okay, so now the question is, could we have come up with this with our shortcut here? So there's our shortcut for these things that are in this exponential form. So let's try. So the first thing that I see is that the exponent is not just a k. So that's a problem. So my instinct would be, first step would be, let's re-index it. Let's re-index it so that that exponent up there is just a k. So to make that just a k, we need to replace the k with something. What should we turn, and if we do that to this k, we do it to all the k's. So we're going to replace this k with k minus 1. So every k that we see is going to turn into a k minus 1. So if this becomes a k minus 1, we have k minus 1 plus 1, which is k. If this is a k minus 1 in the if this is a k in the numerator, it becomes a k minus 1. And then in the denominator, that becomes k minus 1 plus 1, which is just k. How about our index out here? If we replace that k with k minus 1, where does this start? 2. Right? If you replace k with k minus 1, you would add 1 to both sides to get 1 plus 1.
So you re-index the sum.
So we re-index the sum and we get this. Okay, so this has the exact same terms as this. These are the identical series. These are identical. Now we're not quite there yet. We're not in this form yet, but we're getting there. So one more step. So this goes to infinity. This starts at 2. We distribute the k into the numerator. So we get 1 minus 1 over k, all to the k. Now we're in the right form.
That's minus.
the A is -1, and the B is +1. So A times B is -1, so we get e to the -1.
We can do that on the test.
So that would be our shortcut. You can do that if there's a question that doesn't say use the log limit process. So the limit as k goes to infinity of 1, and maybe I'll write it this way, -1 in the numerator there. This will equal 1 over e. So quite frequently you can do some algebraic manipulation to put it in that shortcut form.
How do we notate that we did the shortcut form? Like, because it's not, we shouldn't say log limit because you didn't actually do the long thing.
So if you have to do log limit, you've got to do that. But if you're going to use the shortcut for a homework problem or something,
E form.
you would have to rewrite it so that it looks like this. If you rewrite it so that it looks like that, you know, then I know what you're doing.
Okay.
Yeah.
So you don't have to mark it or anything?
No.
All right.
Yeah. If you get to this form, then I know what you're doing. The worksheet has a handful of these to practice. Okay, what do we have? One more on this page? Okay. Now here, this is an oddball one. Does it converge or diverge? Diverge, because it grows even slower. So the terms are going to 0. They go, the numerator, the denominator is growing even slower than k, so the fractions are going to 0 even slower than 1 over k. Right? 1 over k goes to 0 very slowly. This is going to 0 even slower, because natural log of k grows slower than k grows. So we're going to do a comparison here. We're just going to sort of compare it to this series, 1 over k. This is going to be our b sub k. We're going to choose b sub k to be 1 over k. And this diverges because it's the harmonic.
And we can just say that it diverges because it's the harmonic.
You can say it diverges because it's the harmonic, or you can say it diverges because p equals 1 and p is less than or equal to 1. Yep, either way. So our suspicion, of course, is that this diverges. So we want to show that a sub k is bigger than b sub k. Because b sub k comes from a diverging series, we want to show that a sub k is bigger than it. Let's find out. So a sub k, 1 over natural log of k. I don't know. Is it? I hope. We'll find out. So we get this. Cross multiply. We get that. And this is true. If you were to graph, this is true, and whether we say it's true by inspection or we do a little bit more work, it's kind of up to you. There is what natural log looks like. Here is what, oops, the terrible line. Here is what y equals x looks like, or y equals k, whatever letters you're using. So this is y equals natural log of x. This is y equals x. So now this isn't a formal proof, just looking at the graph. Does anyone know how you would do the formal proof? You can use a derivative technique from Calculus 1. So the k value starts at 3 here. And so if you were to plug in k equals 3, you can verify that that's true. All right, so if you look out here at 3, there we are, there and there. And that's going to be true. What do you think is true about the difference as you go forward? It increases. So if it's true right here, if you look at this function, if you look at k, so if you build a new function, this function right here, this function is going to be greater than 0 when k is 3. And if you take its derivative and show that its derivative is positive, that means that that function is increasing, which means as you go further out, the difference is just increasing. So that means that that this would be true. So a couple ways you could get at it, but graphing, it's totally fine. Those things never intersect. I mean, you could also, see if they intersect or not. You can say that and then see if they intersect or not. Does x ever equal ln x? You try to solve that equation. You won't get a solution. Okay, so that is true. So our conclusion then is, therefore, so this is true. So therefore, both are going to diverge. So both diverge. Since 1 over k, series 1 over k diverges, 1 over natural log of k must diverge.
How far do you want to go for the answer?
Here?
That's fine.
Yeah, that's enough. I mean, this I would say in Calc 2 is you can just say it's true by inspection. If you because you have done enough Calc 1 that you've graphed both these functions hopefully a lot by now, the identity function and the natural log function, and so it's fine to say that it is true by inspection. All right, last slide here, and we'll go do our alternating series. Okay, what do you think this series does? Converge or diverge?
No, that's good.
Here's some conversion. This is what we would let b sub k equal.
Where did that come from?
So we get rid of the insignificant 3 and then simplify. So b sub k is always found by erasing anything that's insignificant and then simplifying. And what is p here?
3.
And that is bigger than 1, therefore converge. So our b sub k series is a convergent series, so we say, oh, a sub k series must be convergent also. So a sub k, b sub k. Do we want the a's bigger than the b's or the a's smaller than the b's? Smaller. Because the b's converge, smaller than converging will converge. So if we can show that this is true, then we're good. So we're going to take our a sub k, which is the original. A sub k, we don't know. We're hoping that this is true. Crisscross. Subtract off the k to the 11th power. 0 less than 3. Still true. Therefore, both are going to converge. Both converge. Both do the same thing. Okay. Let's pause on this one. This one you're going to use a comparison to just 1 over k squared. I want to get going with the alternating series. We can come back and finish that one next time. But I want to have enough time to talk about alternating series. Up to this point, we're pretty much always working with positive term series. The assumption for almost every test that we've had is assume that the terms are all positive. Alternating series means alternating. Every other term is positive, every other term is negative. So very specific. It's alternating. And there's a couple of things that we do when we're talking about alternating series that we have to be aware of notationally. So the first thing that is different, up until this moment, we have said a sub k is everything inside the summation symbol. So up to this moment, we have said that's a sub k. We are going to do that differently for alternating series. For alternating series, a sub k is everything except the switch. So the switch is this part. That's just giving the alternating signs. So for an alternating series, when we talk about a sub k, we are essentially taking the absolute value of everything that's inside the summation symbol. Okay, so a sub k is not everything now. You take its absolute value. You get rid of the switch. Okay. So here is the alternating harmonic. And so the question first and foremost is, does the alternating harmonic diverge? Or does throwing in these minuses offset the growth of this to infinity enough that that would be finite instead of infinite? It's certainly going to be positive, but is it going to go to positive infinity, or is it going to go to some other positive number? All right. So what do you think? If you have half the terms are negative and half the terms, in air quotes, half the terms, we're talking about an infinite number of terms. So if half the terms are positive, half are negative, do you think that that's going to be finite or infinite?
Can't you describe them as two series?
So if you have two series, so if you have two convergent series, you could say that you could do the series a sub k minus the series b sub k. If they both converge, then the series the difference would work. That's true. But what's your gut hunch? Do you think it's going to converge or diverge?
I think diverge.
We hear a diverge. A converge. Let's find out. Okay, so we know that that diverges. So here, we're going to look at the sequence of partial sums like we normally do. So here is s sub 1, and then s sub 2 is this, and then s sub 3 is the sum of the first three. So here we go. So here is the sequence of partial sums. So here is the first partial sum right up there, 1. Where are we? 1. The second partial, so s sub 2 is going to be 1/2, which is right there. Oh, whoops, that's not 1/2. This is 2 right there. S sub 3 is going to be right there. So s sub 3 is the sum of the first three. There is s sub 4, there is s sub 5, there is s sub 6. It actually looks like it's, so if we numerically just start plugging in k values and adding up, it looks like we actually have an alternating series that's converging to a number. So it appears that it might actually converge. So here is our sequence. So here is our sequence. 1, 1/2. So if we were to look at the S sequence, so if we call it S sub n is the sum of the first n terms. So let's just look at that. So it's going to look something. I don't know what the nth term looks like. I can't write S sub n. We know that for geometric and telescoping, we can write S sub n. We can't write S sub n here. But we can say that the sequence is 1, 1/2. We don't have a closed form way to write S sub n in this case. But there's our S sequence right there. So I claim that it's going to converge to natural log of 2. We're not showing that. We're just going to see that it does converge. When we look to that, geometric and telescoping are the only two that we can show what it converges to. It takes much harder math to show that this actually does converge. But natural log of 2 is going to be this number right here. That is ln of 2 right there, that irrational number. So the alternating series is going to converge to that, natural log of 2.
Gee, I wonder where ln2 came from. The answer key.
The answer key. So this leads us to the first test for alternating, the first and only test for alternating series. This is one of the simplest tests that we are going to have of the 10 tests, which is cool. So notice, first of all, that they separate the switch from A sub k. So the A sub k for an alternating series does not include the switch. And here is the alternating series test. In my opinion, it's in backwards order, because this is what you should always be doing in your head, at least first. If the limit of A sub k is not 0, we already know it diverges by divergence test. That's going to be true regardless of whether it's alternating or not alternating. If A sub k doesn't go to 0, if you start adding something to itself repeatedly, diverges. So it makes way more sense to do that one first. Like, why figure out whether the terms are decreasing in magnitude? So here's one of those things where I would say, don't use that word. Let's use decreasing. Non-increasing. So it's not increasing. Let's just go with decreasing. Because to actually create a sequence that is non-increasing but not decreasing would be a pain in the neck. You'd have to use piecewise defined things to make that happen. So it's totally fine. Just think in your mind, the terms of the series are decreasing in magnitude. Right? That's what we want to be thinking in our head. Decreasing in magnitude. So if they're decreasing in magnitude and the limit is 0, that means the series is going to converge. So my suggestion is do this first. Like, why go, this is a headache sometimes to show that the sequence is decreasing. So why go to the trouble of showing it's decreasing just to find out that the limit is not 0? Let's go with the limit first. If the limit's not 0, you know you're done.
So it's converging, granted the fact that the A sub k minus the switch is decreasing and the divergence test
Yep.
fails?
Yep. The divergence test is inconclusive. Yep. That's right. So, now we're not going to formally prove the alternating series test. That takes some higher math. But that is the test. A sub k decreases, limit is 0, done. That's it. So here's the alternating series right there. If we want to show that this converges, we do 2 steps. We take the limit of A sub k as k goes to infinity. A sub k, that's just 1 over k. That limit is 0. Check. All right? So A sub k is 1 over k. A sub k is everything but the switch inside the summation symbol. 2, we want to show that this is decreasing. Okay, so here's what we want to show. So this is the part that takes a little bit more ingenuity. So we want to show it's decreasing. That means we want to show that as we go further out, we have a smaller value. That's what we want to show. And I'll write it this way because when I think about my sequence, I'm thinking of going it this way, right? A sub k plus 1 is further to the right than A sub k. The book will write it the other way, which I think doesn't help. This is intuitive, right? As we go further out into the sequence, the terms are getting smaller. So that's what it means to be decreasing. Go 1 step to the right, you're further down than you were before. You keep going down towards 0. All right? Because we already showed the limit is 0. So we know that each term is getting closer to 0. So now we're just trying to show that it's going down towards 0 in this systematic way. So there's 0 down there. Okay, that's what we want to show. So what's A sub k? A sub k is 1 over k. We don't know if this is true yet, so we put a question mark. A sub k plus 1 is just A sub k with the k replaced with the k plus 1. So we just want to know, is that true? That's all it boils down to. We cross multiply, so we've already done a lot of this type of stuff from the comparison test. We subtract off the k, and we get down to a numerical inequality, and that's true. Now we're done. So that proves, therefore, we have convergence. So if we show those 2 steps, the limit of A sub k is 0, and the sequence of magnitudes, the A sub k's, are decreasing, then we're done. So let's try another one. So with this one, step 1, again, I we'll say do the limit of a sub k first. And a sub k is everything except the switch. What's that limit? 0. Done. That's step 1. Limit is 0. Super easy test. If those magnitudes go to 0, it converges. So let's take a look at the magnitudes. So we want to show that the sequence is decreasing. So if we have a sub k, we go a little further to the right. That's a sub k plus 1.
Should we show what our limits are, number 1, to show that the test is correct?
We showed that this limit is 0.
Well, the limit is x approaches infinity.
Oh, you mean the subscript?
Yeah.
Yeah, we can put a k goes
Or
to
K.
infinity. Yeah.
Busted.
Busted. Busted flat in Boise. Okay. What's a sub k? That's 1 over square root of k. We don't know whether it's greater than or not. We're trying to prove that. So we get this. So a sub k plus 1 is just a sub k with the k replaced with the k plus 1. We crisscross. We square both sides. So standard inequality techniques. Subtract k from both sides. Get down to numeric inequality, and that's true. So therefore, converge. So the bottom line is all of these series that were p series that diverged, if we throw in a switch, they all converge.
That's crazy.
And we had all these p series that diverged because p was bigger, was smaller than 1. And now if we throw in a switch, we're adding enough deflation, we're adding enough negative numbers that it will converge. How about this thing? So here is a fancy way to write a switch.
So we're just never going back to the 10.5 one?
Not today. So this right here, that's just a switch. Do you agree that that's either plus 1 or minus 1? Right? Cosine of a multiple of pi, integer multiply, cosine of pi is negative 1, but cosine of 2 pi is positive 1, cosine of 3 pi is negative 1. So that's just a switch. So here, the a sub k is just 1 over k squared. So to do our test, we first say, what's the limit of a sub k as k goes to infinity? So that's the limit of 1 over k squared, and what's that? 0. So first thing checks. Second thing, we want to show that the sequence is decreasing. So we want to show as we go further out, the terms are getting smaller. So that's what we want to show. So if we switch this over, there is our a sub k. A sub k plus 1 is k plus 1 squared. And then we're going to cross multiply, and I'm going to FOIL this out. So cross multiplication. And then we subtract off the k squared. Subtract off the k squared. Is that true? 2k plus 1, is it bigger than 0? Heck yeah, k is a positive integer. So that we can say is true by inspection. So that's true. So therefore, converge. So that's going to converge by alternating series test.
Just do k plus 1 and square root of that.
Yeah, you could do that. Yeah, that would work also. Yeah. Yeah, so Anna is saying here we have k plus 1 quantity squared. We could have just taken the square root of both sides and then subtracted k. For sure. All right, let's just one more here. What is the limit of a sub k here? What do you think that limit is? So the switch doesn't matter, so we have 1 over k, ln squared of k, that limit is 0. So that's step 1. Step 2, we want to show that a sub k is less than, other way around, a sub k is bigger than a sub k plus 1. So a sub k is this. And we want to show that the terms are getting smaller, so we would want to show that this inequality is true. That's what we want to show. We'll show that one on Tuesday. We'll finish it off. That takes a little bit more work. It's not quite as neat as the ones that we've done so far. All right, let's stop there. Time for a weekend. Week 10's done. See you in week 11. How is that possible? How is that possible? And we'll finish up alternating series on Tuesday. What's that? Oh wait, are we in week 10?
I think we're week 9.
We're week 9.
It feels like week 10. It feels like we're awfully. I hope you're right, because it feels like we're going so far. Yeah, that's why I was just going to look at my online course, because this is by week. So week 10 ends on Monday. You're right, yeah. So we're in week 10. Oh, right. It ends on Monday. So next time I see you is in week 11.
That's pre-calc.
I know.
Does it matter?
No, it's 15 weeks, but it's by the week. Yeah, so week 10 is, we're done with week 10. Shockingly.
Oh no. He's cold.
See you in week 11. See you in week 11. Where are you going?
To Ohio, and the flight's at 4:30.
Oh, God.
Yeah.
Okay, that sounds fine. Or you can email me too, and I can try to.
I tried using Thunderscape and it was still.
Are you going to do something fun?
Yeah, I'm busy.
Yeah, so I
That's usually the go-to.
and then
All right,
as well,
see you on
toilet was
Tuesday.
dirty, so I had to clean it. So a 60-minute job turned into a 5-hour job.
Oh, Project Creep.
Oh,
I was